In this video, I will show you how to solve a system of conic sections. For example, in problem number 6, the top equation is a parabola. I can tell because it only has one variable squared. And the bottom equation is a circle. If I were to put these on the same side of the equation, it would be x squared plus y squared is equal to 20. And when both squared terms have the same coefficient, it's going to be a circle. So we have a circle and a parabola. When you are solving a system and you've got these curves, so there's my parabola, and now I'm going to draw a circle. Now, I mean, there are a lot of possibilities. If I was very unlucky, I might have a circle that had no intersection points with the parabola at all, so this would be no solution. But it's possible that the circle could intersect the parabola at 2 points. So maybe there will be 2 solutions, and that's what we are looking for. We could also have a situation where the circle could just barely touch the parabola at 1 point. So there could be a situation where there is one solution. We are using 2 different methods to solve these systems, substitution and elimination. So the first thing I do is look it over and decide which one I'm going to prefer for the problem. So I don't really think it matters on this problem which one we do. I'm going to go ahead and do elimination and see what happens. So for the elimination method, you need opposites that cancel, and you really want to rewrite everything so it's in the same order. So for the top equation here, I will write negative x squared plus y equals 0. I just switch these around to put the x first. Now on this one, I really need to add y squared to both sides. So then I will have x squared plus y squared is equal to 20. Now notice the y and the y squared, these aren't like terms either. So I'm not even really trying to line them up, but what I'm really going to focus on is the fact that the x squared and the negative x squared, these are opposites that will cancel, and that's exactly what I want. So if I combine these 2 equations, then these are going to cancel. These are not like terms, so I will wind up writing them next to each other. So it'll be like y squared plus y is equal to 20. Now, I'm going to go ahead and get 0 on one side, and if it's factorable, then great. That'll be the first time I was able to factor a problem on this particular assignment. But if it's not factorable, then I'll have to do the quadratic formula, which is what's been happening lately. So I'm going to try to factor it real quick first. So y squared is going to be y times y. Looking at 20, my best bet is 4 times 5. So if I have a negative 4 and a positive 5, that'll give me negative 20, and inner plus outer has to equal the middle. Inner, I have negative 4y. Outer, I have 5y. Add them up, and you get positive y. So, for the first time, this actually factors. What do you know? That's awesome. So, I can find the solutions by setting these little factors equal to 0. So, setting y minus 4 equal to 0, and y plus 5 equal to 0. So obviously here I'm going to add 4 to both sides. I get y equals 4. And subtracting 5 from both sides, I get y equals negative 5. Okay, so I'm going to go ahead and begin to get ready for my solution set. So these are 2 y values that I have. So I'm going to have something, comma 4. And then I'm going to have something, comma negative 5. So I have these y values, but I need the x values that go with them. So I'm going to find that by substituting the y value back into the original equation. In fact, I have to pick. So I'm going to use the top equation because it seems simpler than the bottom equation. So let me just recopy that. So let's let y equals 4 and see what happens to the top equation. So the top equation, maybe I'll just recopy. So I have y minus x squared is equal to 0. So if y is equal to 4, then this becomes 4 minus x squared is equal to 0. So if I were to add x squared to both sides, then I get 4 is equal to x squared. And if I take the square root of both sides, alright, then I'm going to get x is equal to plus or minus 2. Well, that's two solutions for the price of one. So I have to be really careful with it because I got plus or minus 2. So I feel like I should add on to here. So for this y value of 4, I get to use it twice. So I have plus and minus 2. So I have 2 comma 4 and I have negative 2 comma 4. Now let's check out and see what happens if I substitute negative 5 in for y. So let me just switch colors here, and I'm going to be doing y equals negative 5 now. So again, the equation is y minus x squared is equal to 0. So that's going to give me negative 5 minus x squared is equal to 0. Adding x squared to both sides, that gives me negative 5 is equal to x squared. Well, wait a minute. You can't square something and then get a negative number, not in the real number system. So this is not going to give us any solutions. So thinking of it another way, my next move should be to take the square root of both sides, right? But you can't take the square root of a negative number without getting imaginary numbers. So this negative 5 will not contribute any new solutions. So the two solutions we already have are the only two solutions. Alright, in other words, these are the solutions to the system. Let's take a look at Desmos and see how we did. Alright, so you can see we had a circle and a parabola, and we have these two intersection points, negative 2 comma 4 and 2 comma 4, which are the two solutions that we came up with. So good job. Looking at number 7, this is definitely one that would be good to do the elimination method. If I were to multiply the bottom equation by negative 1, which would just change all the signs, that would make this become negative 4x squared, and this would become positive 9y squared, and I'd have a negative 36. So if I go ahead and combine these two equations to get a new and valid equation, these are going to cancel out, and I'm going to be left with negative 16y squared is equal to 64. Now if I divide both sides by negative 16, something magical happens. Alright, y squared equals, I'm pretty sure this is negative 4. Yeah, so you can't square something and have it equal a negative number. Nothing squared is negative. Or thinking of it another way, if I were to do one more step, the next step would be to take the square root of both sides. You can't take the square root of a negative number. You're just going to get an imaginary number. So that tells me that this system has no solution. So we're just going to write none. Alright, meaning there are no solutions to this system. Now, what kind of shape were we dealing with here? Okay, so it looks like we had a hyperbola for the first equation. I know that because one of the squared terms is positive and the other one is negative. And looking at the bottom equation, it was another hyperbola. Again, we had one positive and one negative squared term. So we have two hyperbolas. Let's take a quick look at Desmos.com and see why there's no solution. When you graph the two hyperbolas, they look like this, and sort of one of the hyperbolas is inside of the other. But notice that there are no points of intersection between the two hyperbolas. That's why there was no solution. Okay, the next couple of problems are not really systems of conics, so call it a bonus. Halley's Comet has an elliptical orbit with the Sun at one focus. The eccentricity of the orbit is approximately 0.97. The length of the major axis of the orbit is about 35.8 astronomical units, or AUs. Find the standard form equation of the orbit, place the center of the orbit at the origin, and place the major axis on the x-axis. Okay, so we've got the Sun. Boom. All right. There's the Sun. And then we have Halley's Comet orbiting around the Sun. Let's see. Let's go ahead and throw the axis on here. Okay, so Halley's Comet is orbiting around the Sun, doing one of these. Okay, so here's Halley's Comet. That's the tail. You get it. Now, let's put in the information that they gave us. They told us the eccentricity. All right, I'll come back to that in a moment. The length of the major axis of the orbit is this. Okay, so the major axis is the distance all the way from here to here. So to build the equation, I need the A value. I need the distance from the center out to a vertex. So that is half of the major axis. So what is 35.88 divided by 2? Okay, so that is 17.94. So half the major axis is the A value. Okay, so I've got the A value. So what about A squared? Because that's a thing that I'm going to need. A squared, let's see, I'm just going to take this and I'm going to square it. Alright, A squared is 321.8436. Probably could round this, but for now I'm just going to leave it. So I've got A squared. Now, to make my equation, I'm going to need the B value as well. But all I have is the eccentricity. All right, they tell us that the eccentricity is 0.97. Now, the eccentricity is the C value divided by the A value. All right, I failed when I tried to write that C. Let me try it again. The eccentricity is the C value over the A value. So I know that C over A is equal to 0.97. However, I know the A value. All right, as we discussed, the A value is 17.97. So C over 17.97 is equal to 0.9, no, 17.94. I'm sorry, I'm getting hypnotized by the 0.97. but it's really 17.94. So I'm going to just multiply both sides by the 17.94. Okay, so these are going to cancel each other out. So that's going to give me C equals, and I'm just going to multiply this together. So I got C is equal to 17.4018. That's nice, but again, what I really need is B, or well, B squared. So now it's time to go ahead and use this relationship. C squared is equal to A squared minus B squared for an ellipse. So I'm going to need to square this number right here for my C squared. Okay, so in fact I probably should have just written that down. Let's go ahead and find out what C squared equals. Alright, so C squared is 302.8226. I had to break down and round right there. So let me substitute in C squared and A squared. So I have 302.8226 is equal to 321.8436 minus B squared. So I'm going to add B squared to both sides and subtract 302. So that's going to be B squared is equal to 321.8436 minus 302.8226. So let's just do that subtraction. I'm getting 19.021 for B squared. Now remember that the standard form equation of an ellipse centered at the origin is like this. Well, yeah, so it's going to be x squared over a squared plus y squared over b squared is equal to 1. Where a squared, the a is the distance to a vertex. This is how it'll be if it's horizontal, like this. So I'm just going to rewrite this, but I'm going to substitute in my a squared and my b squared. And I'm going to round to 2 decimal places. So this equation will become, let's see, I think I'll just write this in gray. This equation will become x squared over 321.84 plus y squared over 19.02 is equal to 1. So there's your standard form equation right here. Alright, let's do one more word problem. The first artificial satellite to orbit the Earth was Sputnik. Launched by the former Sputnik 1, launched by the former Soviet Union in 1957. Its highest point above the Earth's surface was 947 kilometers, all right, and that's above point B. And its lowest point was 228 kilometers, and that's above point A. The center of the Earth is one of the foci of this ellipse. Okay. And the radius of the Earth is 6,373 kilometers. Find the eccentricity of the orbit. So eccentricity is equal to the C value divided by the A value. So I need to find, okay, why are my letters disappearing? Eccentricity is equal to C over A. So the C value is the distance from the center to a focus, and the A value is the distance from the center to a vertex. So I need to find both of those things. So the thing that's jumping out at me is I don't know where the center of the ellipse is right now. All right, C is the distance from the center to a focus. A is the distance from the center to a vertex. If I don't have a center, I'm out of luck. So let's figure out what that is. So let's see. 947 kilometers above point B. So this is 947. All right, everything I do will be in kilometers. And 228 kilometers above point A. So this little guy right here is 228. And then the radius of the Earth is 6,378 kilometers. Okay, so that's the radius. Okay, so this is 6,378. All right, and this is another 6,378. Okay, so now we're getting somewhere. So let's find the length of the major axis here. I feel like a highlighter would be appropriate if I can get the right width to use. Let me try this guy. This that I'm highlighting right now is the major axis of this ellipse. Notice I have every segment along the way from one end to the other. So if I add up all of these numbers, that's going to tell me the length of the major axis. So let me do that off camera. Okay, so I added up all of these numbers, and the total was 13,931. So that is the length of the major axis. Now remember, when you're dealing with an ellipse, okay, so if this is an ellipse, if here's the major axis, okay, and here's the center, so this distance all the way across is the major axis, but the distance from the center to the side, or a vertex, is called the A value. That's the A value. I don't know why I put an equal sign, but that's the A value. So, in other words, the A value is going to be half of the major axis. So, if this is the major axis, then the A value will simply be half of that. So, that means that the A value is going to be, let's see, divided by 2, getting 6,965.5 kilometers. That's the A value. Okay. Now we need the C value. So all we need to do is find the C value. Remember that the C value is the distance from the center to the focus. Now, the best way for me to explain how I'm going to find the distance from the center to the focus is to imagine that this entire orbit system is placed on the following XY plane. Okay, so imagine that this is the origin 0, 0 at this point right here. Then that means that, for example, this point right here, this point B, this would be 947, 0. This focus right here, the center of the Earth, is a focus. The x value of this point would be whatever is 947 plus 6,378. Okay, let me just punch that in my calculator real quick. 947 plus 6,378. So the coordinates of this point would be 7,325, comma 0. Okay, now the question is, where is the center of this satellite orbit? Where's the center? Well, remember that we know that the total distance, the major axis, is 13,931. And so the A value, half of that is going to be 6,965.5. So we can use this number right here to place the center on this little number line. So, okay, so it's going to be somewhere between 947 and 7,325. All right, it's going to be somewhere between these two. All right, so I'm just going to put a mark right here. And, you know, so the coordinates of this point would be 6,965.5, comma 0. All right, because that's the A value. That's half of the major axis. All right, so from this origin to the center is the A value. So now we're ready. Now that we've sort of lined these all up, we can now say the distance from the center to the focus. It's the distance between these two right here. This is what we wanted. Boom. Okay, this little, what I'm just coloring in blue, this is my C value. And that C value, of course, all I need to do is subtract. So I'm just going to do 7,325 minus the 6,965.5. Okay, so I'm getting a C value of 359.5, and we already knew that the A value was 6,965.5. So if I do this division, 6,965.5, that's going to give me my eccentricity. So the eccentricity is 0.0516. Wonder, can I make this a fraction? Nope, not really. So there it is. That's my eccentricity. Boom. I just want to comment that eccentricity reflects how circular the shape of the ellipse is going to be. And the closer the eccentricity is to 0, the more circular the ellipse is. So notice that this E value is 0.05. So that's very close to 0, and you can see how circular this ellipse is. On the other hand, when we were doing the previous problem, we were dealing with an eccentricity of 0.97. All right, that's very far away from 0. If you get to 1, that's just playing a parabola. So this is about as far away from 0 as you can get before you become a completely different shape. So notice how this ellipse is very stretched out and non-circular compared to the problem number 9, where the eccentricity is much closer to 0. Alright guys, that's going to do it for this video. Go ahead and click here in the red apple to watch the next video. Click in the green apple to subscribe, or click the yellow apple for the full playlist.